start.
Hey, thank you. I'm very happy to visit today and to talk about these things, about some possible evidence for a fifth force. So when we talk about a fifth force, we're talking about some new boson that communicates some force between particles, and there must be some reason why we haven't seen it up until now, because we know of the four standard forces, however we want to define them. Any force that we haven't seen up until now, it must be because either the force carrier is very heavy, or perhaps that it has very small couplings to the particles that we are used to seeing on an everyday basis. In fact, the Higgs itself could be thought of as a fifth force, as a boson that has couplings to particles, and it fits both of these, that it is pretty heavy compared to the particles of every day, and also has very small couplings to things like the electron and the up and down quarks. Though we'll not talk about the Higgs today, you can imagine that if the particle is not too heavy, then precision experiments can be used to find these particles that have small couplings. And so with that idea in mind, we're particularly interested in looking at some experiments from the ATOMKI collaboration, where they have shown what appeared to be two excesses in their experiments at a level of about 7 sigma in some specific nuclear decays. So the types of their experimental setup, the type of experiment that it is they have some proton beam that strikes a particular nuclear target and produces some particular unstable nuclear excited state. This excited state then decays down to the ground state and in some cases emits a pair of leptons, an electron and a positron, and this pair is then detected. So in kind of more detail, here we have some pictures of the ATOMKI setup. The proton beam would come along this pipe here, and then in the center, it strikes the target, and then these 6 telescopes around the side then detect the electrons and positrons and can measure the angles between them. Of course, like with any experiment, you have to care about different types of backgrounds, and there are a couple of interesting backgrounds that could be could fake this, that you have to be careful about. One is that you can imagine producing E plus E minus pairs during the actual production of the excited state through the radiation of an excited photon. This is so-called external pair creation. Or it could be also that during the decay from the excited state down to the ground state, that either through a real photon or an off-shell photon, you produce an E plus E minus pair, and this would be called an internal pair production. And what the ATOMKI collaboration is claiming that they have seen is that their results are consistent with the production of some new particles, some new boson that they've called X, that is created in these internal pair creation events, so that during the actual decay of the excited state down to the ground state, a new boson is produced that then decays to an E plus E minus pair. So the first thing we need to do is consider these results and these anomalies, and how realistic do they seem. So there are a couple of reasons to take them seriously. One is that they appear to be 7 sigma anomalies on top of what are expected to be smooth backgrounds. They're not some kind of last bin effect, but they're from the region where the detector is expected to be sensitive. The leading backgrounds are well known. They seem to be well known, and in any case, they do not produce these type of bumps. And one thing that's particularly interesting that their collaboration did in one of their experiments, the first experiment when they considered producing excited beryllium states, is that they scanned over the energy of the beam. And as they scan through different energies, you can see that the excess that they're seeing grows as they scan and then goes away, which is consistent with there being some excited state that they're hitting a resonance of, which is producing these new particles. And finally, the electron and positron energies are produced in such a way that appear quite symmetric, which would agree with the idea of a sequence of 2-body decays. The excited state decaying to the ground state plus the X, the X then decaying to an E plus E minus pair. So for all these reasons, the ATOMKI anomalies are interesting and worth taking seriously, and kind of examining what physics and what new physics could possibly be explaining them. So of course, the first and most basic type of consistency we need to look at is just simply kinematics. If we are hoping that both of these, or considering the fact that both of these signals could be from the same particle, the same X boson, then that particle has some specific mass, and we should be able to see if kinematically one particle can explain the two. One can do that without too much trouble, looking at the kinematics, and you can learn a few things that will simplify some of the analysis that you can do. Is you can look at the kinematics of the production of the excited state and its subsequent decay, and you see quickly that the excited state is not moving very fast from this production event, and so we can, for all practical purposes, take it to be at rest. Similarly, the electrons, even though these are not high energy events, they're kind of high energy compared to the electron mass, and their velocity is essentially 1, so we might as well take them to be massless. And then this X boson, if it really is at about 17 MeV, as the ATOMKI collaboration seems to indicate, then its velocity is neither 1 nor small, and we kind of have to keep track of all the different effects. But so what we can do then is just consider the simplified state and see what we see. You can analyze the excited states based on their spin and parity. And so you see here in the beryllium case that we're interested in, we have the excited states are both axial vectors, 1 plus vectors, or spin 1 with parity plus. Of these two, it is the 18.15 state, which is associated with the anomaly, which is a much wider state. And then in the helium case, there's actually two excited states that are interesting. One is a scalar, the 0 plus, the lower of the two states, and the higher state is a pseudoscalar, a 0 minus. And both have somewhat comparable widths. Both of these, because of their difference in parity, we will see are quite interesting for discriminating possibilities what this X boson might be. We'll also consider a little bit the possibility of a carbon state, carbon 12. I should emphasize that the ATOMKI collaboration has not studied the carbon system, or has no results for the carbon system. And so we are just including it because simply we have already looked at the 1 plus, the 0 minus, and the 0 plus states. And so we're using the carbon system because the excited state is a 1 minus state, or has a 1 minus excited state, that can help us to kind of check all the possibilities of the spin and parity of the excited states to help diagnose what the spin and parity of the X boson might be. So this is, but even if the carbon state isn't used, one could imagine using the same ideas for a different vector-like excited state. So let's return back to the idea of kinematical consistency, checking that both of these results could correspond to the same boson. In the rest frame of the X particle, of course, the electrons that it decays into are produced back to back, and we could simply parameterize them in this way. They're 4 vectors, where here this angle theta is simply the angle that the electrons make with respect to the direction of the X boson in the lab frame. If the electrons are aligned exactly with the direction of boost, then they remain back to back in the lab frame. And this, of course, is the maximum angle that could be between the lepton pair. On the other side of things, if the electrons happen to be perpendicular to the boost direction, then they'll both be bent in when you boost to the lab frame, and this will be some kind of minimum angle that the electron-positron pair makes in the experiment. What one can also find is that the spectrum of all the angles, or the distribution of angles, is peaked towards this minimum angle. If you look at all the possible populations of what the angle might be, you have many more electrons that are closer to the minimum opening angle than would be just exactly parallel with the boost angle. And so, for instance, you would expect to see the dominant or the most of your signal closer to the minimum angle rather than to the largest opening angle. And this is interesting because then you can start to see where you might expect the signal to move if there's a single boson that's responsible for both of these effects. For instance, in the beryllium case, you see the minimum angle is around 140 degrees. And indeed, the opening angle where the maximum of the signal is just a little bit above 140 degrees, which is kind of consistent with this idea. So if you believe that to be correct, then if you look in the helium system, you should expect then the dominant place of the signal would be at a much lower angle, something closer to maybe 115 degrees. And indeed, you find in the helium case that the maximum of the signal is much lower, somewhere in the neighborhood of 115 degrees. To make it a little bit more explicit, we can make simply a plot in terms of the excitation energy between the excited state and the ground state and the minimum opening angle between the electron-positron pair. And then we can plot contours of the mass of the X boson, where those lie in that space. And you can see here that in the excited beryllium case, that they lie kind of around the 17 MeV contour, and that as you move to helium, again, it is close to this contour of about 17 MeV. You can also see here that this experiment was run in between the two excited states in helium, and we'll come back to that later. But one thing that's also useful about the fact that there's now two signals is that if you were concerned that the first signal might be due to some kind of unknown systematic having to do with the detector, the experimental detector, the fact that the signal has moved when you change the nuclear state that you're considering should eliminate many sources of systematics that you wouldn't expect, for instance, the detector geometry to have this type of effect. So this again is another reason to take some of these, signals seriously. So what I hope I've shown so far is that there is some very basic consistency, kinematical consistency between these two events. But of course, that's not enough. We need much more than kinematical consistency. We need that there's some kind of particle dynamics that agree between the two cases. The hope is that with this information from the two experimental systems, we can either check and find that there is no particle interpretation that explains the two, and so there's something else going on, or that there is some narrow range of different particle models that would explain this signal, as we use both of them to narrow things down. And as we will see, that this is the case, that some very simple ideas can already be put in tension from these two kind of preliminary measurements. So we'll start with just a simple analysis to organize our thoughts with spin and parity. I already talked about how the different nuclear excited states can be organized in this way. We will also consider several possibilities for this X boson as being either a scalar or a pseudoscalar or a vector or an axial vector. And already you can start to see that each of these situations is different and interesting, and different kinds of constraints might be applied to them. For instance, if you look at the beryllium result, just spin and parity already tells you that the X boson cannot be a scalar. It just can't produce the result. So if it's spin zero, it must have at least some pseudoscalar component. But if it is a pseudoscalar, then you see that in the beryllium case, its decay is p wave, whereas in the helium case, it's s wave. And so you might then expect that the decay widths of the two would be, or could be, quite different, just because of the different partial widths that are dominating the decays. The same is true for the axial vector. In beryllium, it would be an S-wave decay that dominates, and in helium, it would be a P-wave decay. However, if it's a vector particle, if X is a vector, then in both cases, it's a P-wave decay, and so you might expect that the widths are somewhat similar. You can also see here that the two different helium excited states are sensitive to the two different kinds of parities, and so if we're able to determine which of the helium states is giving rise to the signal, then we can already say something interesting about the parity of the X vector. So what we'll do, and the rest of this talk, is to try to examine some of the dynamics, the actual particle dynamics that we can put on top of this simple spin parity analysis. Of course, we're going to need more than just spin and parity. We're going to need the full machinery of quantum field theory. And so what we'll do is we'll use an effective field theory where each nuclear excited state is composed of, or is described by a distinct quantum field. And we'll be able to look at the interactions between them. Of course, this will include all the spin parity results inside of it, but we'll be able to get much more. We'll be able to actually calculate decay widths and things like this. Now, this basic EFT is an EFT of nuclear states. We want to be able to compare to other experimental results, and most of those in particle physics, or in the kind of the broader picture of particle physics, have to do with more basic couplings to more fundamental particles, not to nuclear states, but maybe to nucleons or to quarks and leptons. And so what we'll also do is match our effective field theory, our nuclear effective field theory, to nucleon couplings so that we can compare constraints from the ATOMKI results to other experiments. And what we'll find is that we're able to specify decay widths very well up to unknown nuclear coefficients between the different nuclear states. So this is a limiting factor in many of these particle possibilities, except again for the vector x. The vector x is special in that there are nuclear decays to photons, and of course the photon is a vector. And so oftentimes we can compare the X boson decays to the photon decays, and the unknown nuclear physics will divide out, and so we can say things that are more precise in the in the vector case. So let's start with the simplest case that I already mentioned. If the case of X is a scalar. Sorry, was there a question?
Yes, please.
Mm-hmm.
Just before, I'm Wagner from KIES. Mm-hmm. Before you move to the theoretical analysis. And I'm sorry for not being too specific about my question, but I remember that in your first paper when you announced the anomaly, I guess back in 2016. Is that correct?
This is actually my first paper on it, but some of my collaborators, yes, worked on it back in 2016. Mm-hmm.
And I mean, if I'm correct, there was one specific, can I say, a problem, let's say, related with the Beryllium decay, which was the anomaly could be seen in one state, but could not be seen in another excited state. Is that correct?
That's right. So the anomaly was seen in the 18.15 state. So I just listed them here. But it wasn't seen in the 17.4. And that's a good question as to why that might be the case. There is one issue you can look at between the two states, is there's about a factor of 10 in width. The lower state that it wasn't seen in is much more narrow. So one possibility is that the ATOMKI's collaboration's energy, their energy precision was not sufficiently tight that they could actually be right on resonance, and so they didn't have enough kind of data to see the results. Or there could be some other type of physics that's going on, something having to do with the different isospin of the two different states, or different types of models say different things. So I agree, this is a question that in my mind is still unresolved, but I don't have enough information to say anything too precise about it. I will say that the places where they have seen the anomalies, in Beryllium and in the Helium case, the widths are all quite a bit bigger. So the smallness of the other width is a possibility, though it may not be the answer.
Okay, thank you.
Sure. Okay, so for the scalar X, a simple possibility, but unfortunately is ruled out. At least if we're assuming that X has definite parity, then it cannot explain the Beryllium signal, so we'll not spend any more time on it. So let's move on to the pseudoscalar. We want to make these concrete predictions where we are relating to other experiments. And so we'll consider writing the couplings of the X boson in this way. You might first think of simply writing down some coupling to protons and coupling to neutrons in this simple way. But we could also rewrite that as a coupling to the iso singlet current and the iso vector current. where the isosinglet current simply preserves isospin, and the iso vector changes it by 1 unit. And these are simply specific linear combinations of the couplings to protons and neutrons. Now, to leading order, at least for the leading order I will talk about right now, the beryllium decay is isospin preserving. It goes from isospin 0 to isospin 0 for the higher excited state. And so then we can simply imagine writing the amplitude in a simple way, where we write some coupling to the iso singlet current between the excited state and the X boson and the ground state. And so then our amplitude is simply, some factor, the sum of the couplings, times this nuclear matrix element between the excited state through the iso singlet current to the ground state. Okay, so that's kind of the nucleon amplitude. We can now compare that to the nuclear amplitude. So this is just what we had before. If we look at the nuclear EFT, then the dominant coupling for this decay of the excited state through a spin 0x, a pseudoscalar x, is simply this one, where we have an axial vector, and so we can just couple to the derivative of a pseudoscalar with a scalar ground state for our leading decay. We can then find the amplitude in a similar way between the excited state and the ground state, including our operator, some Wilson coefficient. And then for simplicity of comparing, we'll include as a part of our definition of the Wilson coefficient an extraction of a coupling of this type. By doing that, we can then make this identification, by computing the amplitude in the usual way, between the Wilson coefficient and the unknown nuclear matrix element that would exist in the system. And what our assumption is for this work is that these Wilson coefficients are roughly order 1 in kind of the units of QCD. Okay, so now that we have this idea, we can simply calculate that was in the beryllium case that we calculated. We can do the same thing in the helium case. It is again an iso singlet transition from the excited state to the ground state. And so it has the same type of form. In the helium case, because the excited state is also spin 0, you have a simple operator that mediates the decay, and you can calculate in this simple way what the amplitude has to be. And then you, of course, can calculate the decay widths in terms of these unknown C coefficients. Then the interesting thing is you can then take the ratio between the beryllium and helium cases, which is presented simply here. And the point is that what you find is that the ratio is quite small. With the beryllium width, you'd expect to be almost a factor of 1,000,000 times smaller, assuming that the C's are of the same order, and that the with this definition of the cutoff being around the GeV scale. Now the experiment, I put an asterisk here because their calculation of the width in the helium case is perhaps not quite finalized, but they have motivated at least that the decay widths in the two cases are roughly the same. And so what we take this to mean is that it seems like the pseudoscalar case is highly disfavored, at least this simple type of pseudoscalar. I should point out that this particular assumption for the pseudoscalar, or the assumption we've made is there's nothing special about it. If, for instance, you assume that the pseudoscalar is an axion-like particle, then of course this operator cannot exist because it's not shift invariant. You need to have some derivative acting on the x, and so then the relevant operator would be, I think, dimension 5, and you have you don't have the same type of claim that you can make. And so there are models with a axion-like X boson, which don't have this same tension. But this is the claim that we make for this type of pseudoscalar. So we can then do the same type of analysis for the axial vector. We write the current in terms of a isospin preserving current and an isospin changing current. You can calculate what the leading order operator is, or determine what the leading order operator is for the beryllium decay and also for the helium decay. And you find a relationship between the C's and the different dominating operators. Everything is just the same as we did with the scalar case. And then you can make the same type of ratio. And here you find that the ratio is not nearly as large. It's maybe a factor of 100. And so this seems like it could be borderline consistent with current measurements because of the uncertainties involved in the Cs, the nuclear matrix elements, and in the measurement of the width. I'll point out also that if you were to use the carbon case, because in carbon it's an isospin changing current, you actually have some sensitivity to the specific proton and neutron couplings, in that the beryllium is sensitive to the sum of the two, whereas carbon is sensitive to the difference. And so if ATOMKI or some other experimental group were to measure a different system where the excited state is has non-zero isospin, or the transition from the excited state to the ground state is isospin changing, one can imagine trying to extract these specific couplings, the proton and the neutron couplings. Okay, so let me turn to the vector case, which is a little bit more interesting because we can say things with more precision. Much of the form of what we'll do is the same, but there are some slight changes. When we're defining the X current, because we're interested in comparing to the photon current, we will include factors of the electromagnetic coupling E, but everything else is the same. You can write the current in terms of an isosinglet current and an isovector current, just including this factor of E, so that we can compare it to the photon current, which is simply this in terms of the same. And then what we'll see is that nuclear factors that match the excited state to the ground state in terms of these different currents will be common to both the X decay and the photon decays. And so as we take the ratio between them, much of these unknown physics from the nuclear matrix elements will divide out. Let's start with the beryllium case. In beryllium, the leading order operator is this one, because the excited state is an axial vector and X is a vector. You need to couple with the epsilon tensor to preserve parity in the decay. And so you can use that to calculate what the decay is in the vector case. But notice that this is actually the same operator that you would use for the photon, because this operator is, if you like, accidentally gauge invariant, which is to say that because the epsilon tensor is antisymmetric, you can rewrite delta alpha acting on X as simply a kind of a field strength type of form. And so when you compare this for the photon, this is also the leading operator, and it's very simple to compare the photon and X decay widths. And what you find is that the ratio of the beryllium decay to the photon decay is simply up to the sum of these couplings, and then basically the phase space, and the fact that X is massive, whereas the photon is massless, at least in the simple analysis that we've done. As was mentioned in the question earlier, there was a paper analyzing the beryllium decays back in 2016 by this group down here. And they found that there is actually experimental evidence for some isospin mixing and possibly isospin breaking in the beryllium case. And they tracked those effects carefully and found that actually the ratio of the widths is modified in that case. But you can see how the form is very much similar. Much of it just comes from a change in phase space, though because of the isospin mixing, you have different coefficients acting on, if you like, isospin preserving and isospin breaking terms. The isospin preserving and isospin changing terms. And if there's isospin breaking, there can be additional terms as well. So I will not derive these for you, but I'll simply point them out because we will use all of these forms a little bit later when we're comparing with the helium case, which we will discuss now. So in helium, the X decay is mediated by a very simple operator, and you can go through the same process that we've been talking about this whole time. However, you can see immediately that if we were to replace the X boson by the photon, that this operator would not be gauge invariant. And in fact, the leading photon operator, leading gauge invariant operator for a photon decay is this one here. Now, this is an interesting operator, the so-called E0 operator, because it mediates a decay not to an on-shell photon, but directly to the photon current. As you can see, if you take this and integrate by parts from either one of the fields, because of the antisymmetry of F, two derivatives acting on the other field will simply vanish, and you just get the derivative acting on F itself. And by using its equations of motion, you can replace that by the current. And so you find that this leading order electromagnetic transition is in fact basically this transition where you go immediately from the excited state to the ground state and an E plus E minus pair. So whereas in the helium case, we could compare directly to a two-body decay in beryllium to a two-body decay in helium, here we have to compare a two-body decay in helium of the excited state to a ground state and the X boson to a three-body decay of the excited state to the ground state and an E plus E minus pair. However, we can relate these operators without too much trouble by simply taking the E naught operator, but instead of writing it in terms of F mu nu, write it in terms of X mu nu, kind of the equivalent field strength for the X vector. And remember that the equation of motion for the X would be similar to that of the photon, but with a mass term. And so if we were to integrate this one by parts, then we will find a term that goes like this, where this is exactly the operator we saw before as the leading order operator that mediates the X decay. But now we have an understanding of how this coefficient comes about. So we can then relate the coefficient we had for the X decay to the photon's E0 decay by simply this factor. And that allows us then to relate the two decay widths, and we can find that the ratio of the helium decay to the E naught decay is simply this, where there's no subtlety with isospin mixing or breaking in this case. And we also point out that this E0 width has been extracted experimentally from inelastic scattering of electrons with the helium system. And so up to some uncertainties, we know what the E0 transition is. And so then this constitutes, if you like, a prediction for what the X decay width in helium would be given the constraints that exist from the beryllium system on the couplings of the X boson to protons and neutrons. So what are those constraints? Well, as again was outlined in this paper by this group in 2016, there are fairly strong constraints on the coupling of a new light vector to protons. Come from the NA48/2 searches, where they have a pi naught decaying to an X boson or some new vector and a photon. And these essentially show that the absolute value of this coupling has to be smaller than about 10 to the minus 3. There is a weaker bound on the neutron coupling from lead neutron scattering that needs to be smaller than about 2 times 10 to the minus 2. And then when you actually look at the ATOMKI results, they favor nucleon couplings, the sum of the two couplings, on the order of 10 to the minus 2, which would include that, or kind of imply that the neutron coupling has to be nearly saturating its bound, and that due to this restriction on the proton coupling, that the coupling to neutrons is much bigger than the coupling to protons, and so these authors called this type of vector protophobic because of its strength of couplings to neutrons rather than to protons. So with that in mind, then we can consider those constraints on this ratio of decay widths and see what types of measured decay widths would be consistent with the beryllium result. So again, just using the numbers that we had before, we can say that the width, the predicted width, or sorry, I should say that the experimental collaboration has measured, in a certain sense, the width in the helium case. And if you fold in the uncertainty of, and they also normalized their measurement to this E naught transition. And so we're just folding in the uncertainty of the E naught transition with the number that they quote to give this value for the width. But we were also in communication as we were working on this paper with them, and they mentioned that there may be another kind of subdominant background, an E1 transition that they were still thinking about and trying to model, which could modify the value that they get for their width. And so there's probably some extra uncertainty on what this value is. And so what we'll do is just take it as take the beryllium result as kind of a more definite width and see what sorts of widths in the helium case would be consistent with that. And this is what these plots are here to convey. The plots are here in the, this is the coupling of the, this is the neutron coupling of the X boson, units of 10 to the 3. And this is the mass of the X boson. And then here on the top, we have two different possibilities for what the proton coupling is, kind of as large as it can possibly be and as small as it can possibly be, just the negative of it. And so in the shaded blue region, we simply have the region that's favored by the beryllium experiment. And then what these black contours are here, they're contours of the ratio of the widths, the X width to the E naught width, normalized so that we have kind of order 1 numbers here. And so if we just look at the kind of the most basic analysis that we first did, you would see a range between about 7 and about 1 for this possible ratio. If we include isospin mixing and breaking, then things move around a little bit, and you see you go from about 11 maybe down to about 3. And so we can translate that into our prediction. We would say then that from helium, we would predict that the decay width, from beryllium, we would predict that the decay within the helium system for a protophobic X boson would be something in the range of 1 to 11 times 10 to the minus 2 times the E naught width, which would give you something like 0.3 to 3.6 times 10 to the minus 5 EV. So this would be our theoretical prediction. And then we note that this already overlaps with the measured prediction, where measured is still uncertain, the measured prediction from the ATOMKI collaboration. So this is somewhat tentative because of the uncertainties involved, but it's already quite interesting that in this vector case where we don't have any uncertainties due to nuclear physics, that there seems to be a possible overlap between the experimental results and the theoretical prediction. And I'd like to emphasize that this is quite non-trivial. This didn't have to happen. This is not something that was obvious when we started. And I'll point out some of the many differences between the beryllium and helium systems. The excited states are different. One's an axial vector and one's a scalar. The beryllium experiment ran on resonance for a particular excited state. The helium was in between two resonances. The operators that dominated the X decay were quite different in the two cases. In the beryllium case, the signal was normalized to an on-shell photon decay. To the helium case, it was normalized to this off-shell E naught transition. And in the beryllium case, there was isospin mixing, and in the helium case, there was no isospin mixing. So they're quite different systems, even though kind of naively they seem similar. And so the fact that they agree is a pretty non-trivial and very interesting result, we think. I'd like to point something else out about the helium case, where there's an additional opportunity here. The ATOMKI collaboration seemed most interested in exciting the 0- state, the higher energy state. But they were unsure of their backgrounds as they moved to higher energies. And so they decided to not run on resonance, but run kind of up some level up the Bright-Wigner distribution for the helium case. And they also normalized their signal to the E0 transition, which comes completely from the lower excited state. So they're kind of in between the two. However, if is indeed a vector, this protophobic vector that is responsible for this new signal, then one would imagine that running on resonance on the lower state would enhance the signal quite a bit. And in fact, more generally, if we imagine that the vector is some linear combination of vector and axial vector, that it's not a parity eigenstate, you can imagine scanning along the Bright-Wigner and finding a particular dependence on how the widths change. And this is what I mean. If you imagine that all the events that have to do with the X boson come from the X cross-section, and all the events that come from the E0 transition come from that cross-section, then in the ratio, you would have a piece that is independent of the energy at which your proton beam is running, because both the signal and the E0 transition are normalized at the same point on the bright Wigner, sorry. So this piece would be independent of the center of mass energy of your experiment, whereas any piece that had to do with the higher state, the pseudoscalar state, would depend where you were running, because it would depend where you are on this bright Wigner versus where you are on this bright Wigner for the two cases. And so you'd have some much more complicated, well, not too complicated, but some non-trivial dependence on the center of mass energy, multiplying the ratio of the two widths, or the ratio of the 0 minus to x decay over the E0 width. So if the experimental collaboration was able to scan in the energy, they could presumably check to see the form of this ratio. If it remained constant, then you would have some strong indication that all of the signal is coming from the 0 plus state, which would say something about the parity of the x vector, or of the x boson. Or if it followed this form, you'd have strong indication that it was all coming from the 0 minus state, and that it was either an axial vector or a pseudoscalar, like an axion-like particle. Or in general, you could imagine fitting this form to whatever you found to extract both of these ratios of decay widths if it has both couplings to the axial, the vector and axial vector cases, to both kinds of parities. So this has not yet been done, but we have recommended it to the people at ATOMKI, and they have told us that they are already looking at running on the lower resonance to see what they can see. So as I'm coming to the end of my talk, I'll say that the current experimental results are quite interesting, perhaps even tantalizing. Of course, what we really need is for another group, more than one group, to check these results. And which is my understanding that there are at least one or a few groups that are working on this. I also think it's quite interesting, the idea of running the helium experiment on the 0 plus resonance, or scanning over the bright Wigner in between to try to determine the parity of the X boson, which, as I mentioned, ATOMKI is already looking into. And for all these results, we'd like to be able to say things with more precision, and as ATOMKI has pointed out, additional theoretical work could be done to more accurately simulate and predict some of the backgrounds related to the production of these states. And so that's an additional project we're looking into, is to how to better simulate some of these backgrounds so that more precise widths can be extracted. And of course, the idea of using different excited nuclear states would be useful. For instance, like I pointed to with carbon, to really test the individual couplings, what the couplings are to the proton and the neutron, to see if the protophobic hypothesis is really correct. So kind of in summary, I would say that nuclear transitions are a natural place to look for MEV mass particles with small couplings to the standard model, as might be motivated by dark sectors. And a few years ago, back in 2016, the ATOMKI group discovered a new resonance structure in beryllium that doesn't appear to be related to standard model physics. And then more recently, at the end of 2019, they found a similar structure in the helium system. What I've outlined today is that using a theoretical analysis of analyzing these two different structures, we see that a spin 0 particle has to be axion-like if you want it to be able to explain both of these signals, and it's kind of borderline consistent for an axial vector, but that there is an impressive agreement for a protophobic vector in both cases, that it could explain both the beryllium and the helium case. But of course, we're looking forward to future experiments and further theoretical work to say more about these things. Thank you.
Thank you very much for nice talk. So, any question or comment?
I have a question. Thank you very much for very nice overview. But you have not mentioned any specific particle physics models for protophobic gauge boson, protophobic X mu. So could you add a few words about the particle physics model for protophobic interest?
Sure.
Yeah.
Yeah, so I suppose there you make a good point. This is kind of part of the work that hasn't been done. I wouldn't say that there are any very very attractive top-down models that I know of. There are things that you can imagine where you have a particular type of coupling that then is played against a kinetic mixing that would kind of cancel the effect in the proton and not in the neutron, just because of course the photon only couples to the proton and not to the neutron. So there are types of models where you can imagine that. There you do have to worry about other constraints that I've not talked about on the lepton sector. I didn't talk at all about constraints that might exist for the lepton couplings and also for neutrino couplings, which are quite constraining, I would say. There's an experiment, for instance, NA62 at CERN right now. Oh, sorry. At NA62 at CERN, where they are specifically trying to measure or trying to find evidence for this boson through its electron couplings, and they have probed about half of the parameter values that were kind of allowed from the initial analysis, and they're planning, of course, to probe more in that degree. So that's kind of one possibility, but all of the models, you have to be careful of not just the protophobic part, but also the electron structure, the lepton structure.
Thank you.
Another question or comment?
I may miss the point that can you show us the effective potential for this fifth force?
The effective potential, I'm sorry?
You mean that this new spin 1 boson mediate a new force, new fifth force. So what does this effective potential looks like?
Well, it would depend on the kind of particle that it is. So here I'm not really, this isn't a statement about kind of fifth force experiments. Usually those are looking for very, very light particles. So here, because of the MeV mass, the range of the force, if you like, would be quite constrained. And it would depend on whether it's a scalar or a vector, of course. So most fifth force, kind of your traditional, I would say, fifth force kind of constraint plots from like astrophysics and things don't apply to masses that are this large. So the notion in which it is a fifth force is just that it's a new boson. You would say that any new boson that we'd find would mediate a force between particles, and so it would be a new force, just like the Higgs mediates a force that's not, weak nuclear or strong nuclear or gravity or electromagnetism. So it's that type of understanding of force, and so it is a bit confusing, but that's kind of the way people talk about it.
I see. Thank you.
Sorry, may I ask a question?
Sure.
Yeah, so the X boson could be modified the the energy level of the helium atom. If the the energy transition, some hyperfine structure being very precise measurement for the helium, would that modify this energy level of the helium?
I don't know that it would modify the actual, you're talking about the actual, like, where the excited states are, the energy states exactly?
Yeah, some photon spectrum of the helium, yeah.
Okay, so let me, if I'm understanding, I don't think it would change when the energy levels are, because those are determined by nuclear physics dominantly. And so I believe that the states would be the same. you're right in that you would expect to see changes in the decay width of each excited state. But because the couplings of the X boson are so small, the changes to the width are very small compared to the nuclear decays. So the nuclear decays really dominate the width, and then there's this small difference from the X boson, even smaller than the photon widths typically. So you're right. That's definitely a change, but it's a small change.
Okay, I see. So how about the helium with the electron energy levels around the helium atom? I mean, it can exchange the X boson between the electron and the nucleus.
Yes, I suppose that is true. But again, that force would be, if you like, be much smaller than the electric force, right? If you looked at whoops. At the couplings that we're looking at here, they're on the order of 10 to the minus 2 or 10 to the minus 3. That's on top of the electric coupling. So this is 10 to the minus 2 smaller. It's 100 times smaller than the photon coupling.
I see. Yeah.
So it's a much weaker effect, and also it has a mass, and so there's a kind of another reduction from there. So I think you're right, but I think these are very, very small effects.
I see. Okay, thank you.
Okay. Any other question?
Hello, I have just a minor question, but I wonder about the BBN bound, because normally this kind of MEV-ish particle will be subject to BBN bound. So if you have any comments.
So I'm not exactly sure which BBN bound you're referring to.
Like the delta N effect there. No, delta N effect.
Right. So the lifetime of X is quite small because they're producing it and seeing it in the experiment. Its decay length can't be larger than about 1 centimeter. So it would decay, if it was produced in the early universe, it would decay long before BBN. So, and its mass is, not zero. It's higher than the electrons. It's much higher. Well, not much higher, but several times the mass of the electrons, and so its contributions to ineffective would be also very small for that reason. By the time you come to BBN, it's not contributing much to the thermal bath.
You mean that because the coupling is too weak to be maintained in the thermal bath until the BBN?
Right. So yeah. So BBN is happening at around an MeV right. So it's by then it's so it's a combination of its coupling and also of its mass. That it's already kind of getting down into the tail of its Boltzmann distribution, so it's just not contributing very much at that point.
Thank you.
Okay. Question or comment? Okay. If not,
I have one more simple question about the minimum opening angle dependence on this nuclei. I think that looks very interesting. In fact, and maybe other physics cannot mimic that one, right?
Yeah, this was the first thing we looked at when this came out to see if it could be true. So yeah, we found this quite compelling. That when we just looked at the basic kinematics, that's right. That it really looks like a particle. So for us, this was a big deal. Like, oh, we should look more carefully at this.
Okay, good. Thank you for a nice talk.